So titrations are the typical way that we react acids and bases, and we can tell a lot of information from titrations. We can neutralize an acid with a base with an acid, but we can also get other information. We can judge the strength of the acid or base based on how much we use and based on titrant curves. So let's get some terminology down when we talk about titrations. So we typically use titrations. We use a burette. That's a really poor image of a burette, but we kind of know what one looks like. The burette holds what's called the titrant. So what we're titrating with is called the titrant. It's the burette. We have a control here called the stopcock, which isn't labeled on this. And we have a flask. Typically we use Erlenmeyer flasks to do titrations in so that we can mix them and mix the solution here. The flask contains the solution that's titrated, also contains the indicator. So maybe a little bit better image here. Typically, if we're carrying out titration, one of our first titrations actually, what we'll do is we'll take a relatively weak acid and we'll add a certain amount to an Erlenmeyer flask. Now notice this is being measured very accurately with a pipette. So we'll use a graduated pipette. We'll put in exactly maybe 20.0 milliliters. Normally at that point, then a couple of drops of indicator are going to be added, maybe some water to dilute the solution slightly. Now notice at this point, if we add water to this, it dilutes it, but it doesn't change the amount of moles of acid. So we can add water without changing the number of moles. The number of moles is still going to be the same. Then what we'll do is we'll take a standardized, typically NaOH solution, a strong basic solution, if we're trying to determine, say, the pKa or the concentration of a weak acid, and we'll add it until we see a color change. Now, the color change, and only till for most of our color changes, we just want the slightest color. Now, for the vast majority of the titrations that we're going to use phenolphthalein. Now, phenolphthalein looks like this. Again, we've talked about it already, but this is an acidic solution, so if we add our weak acid, and then we get the slight pink, that means it's basic. And so at that point, we'd want to stop our titration. Again, we want the slightest bit of basic color, that pink color, as possible. If we can go just a drop to change a pink, that would be perfect. You do have to be careful that sometimes, like we've said before, if you swirl this, that pink color will go away. Now, obviously, if we shake it and swirl it really hard, we're going to get some CO2 dissolved in, and that's going to, mix with the water like we've talked about, make some carbonic acid. H2CO3. Now, we don't want that, so we have to be careful that we mix this, but not too vigorously, where we're actually dissolving some CO2 in and changing that the contents of the solution. Now, there are other indicators. There's a whole range of indicators. Most of them work just based upon the concentration of hydrogen ions. Notice for this one in particular that they're looking at in acidic solutions, if you add more hydrogen ions, those hydrogen ions will attach to the indicator. They'll cause the indicator to change color. In basic solutions, well, there's going to be hydroxide or something that will take that hydrogen ion away, and it will break it up into this form. And so we have just two different forms. Normally, they're going to interact with the hydrogen ions that are in solution. Now, your book has a whole range of different indicators, and here's the interesting thing that we might not have thought of before, and I'm not going to show you all of them or remember all of them right now. If we need them as a reference, we can always look at a table. Notice for these indicators, it says that we use them for different types of reactions. So for strong acid, strong base reactions, it's suggesting methyl red. It is also suggesting bromothal blue. Now, you'll notice that with some of these, getting the right color can be a little bit more difficult. Phenolphthalein is really nice because it's clear or pink. Bromothal blue can work well, but notice it's yellow on one side if it's acidic, or blue if it's basic, and green if we're right in the middle. Well, to kind of tell what's green or a dark yellow or just a slight blue is sometimes kind of difficult if we have a kind of a range of colors. And so for most of our titrations, we're going to use phenolphthalein. But again, if we are just doing a strong acid and strong base, these might be a better choice. And they're a better choice because of where their changes. So they don't all change right at 7. So we like to think of indicators all changing, boom, right at a pH of 7, going from acidic to basic. Notice they have different scales that they change on. This one changes from 4.4 to 6.2, 6.2 to 7.6. Notice this one changes in really acidic conditions, 3.1 to 4.4. And so the range of our indicators is all different depending on which type of indicator that we're using. So depending on the type of titration, we have to choose the indicator that suits our purpose for that. Let's not worry too much about that right now. Once we get to that point, it'll be easy enough to pick off the indicator that we need. So in this one, it's showing us bromothol blue. Again, we don't need to remember which indicator we're using at this point. And notice it's going from yellow in acidic conditions to blue in basic conditions here. So what this is what we're going to be constructing in a lot of our titrations, is a nice pH curve. Notice what they are doing is in their Erlenmeyer flask, on the bottom here, they have an acid, and they're adding from the burette as their titrant a strong base NaOH. So this is a strong acid down here, maybe say HCl. They're titrating it with a strong base, maybe NaOH, and they're titrating it through what's called the equivalence point. So notice what happens here. Because we have a strong acid, notice where our pH starts. Our pH starts very, very low, very close to 0. Notice this is the amount of NaOH that's added. Notice as we add NaOH, the pH slowly rises as the NaOH neutralizes the acid that's there. Once we get to a certain point, notice what happens. That pH spikes. We have a nice big spike, and then it slowly plateaus again. And it'll plateau off at whatever the pH of the strong base is. So we have a couple points we can identify on this graph. One is the equivalence point. The equivalence point is where we have the equal amounts of acid and base. So that's our equivalence point. It's the inflection point of the graph as well. So the inflection point is the point when the graph changes slope. So we are increasing this way, and then we switch and we go this way. That's the inflection point of our graph. That is the equivalence point. And notice with a strong acid and a strong base, the pH at the equivalence point is 7. Now again, that's not always going to be. And again, at 50 milliliters, assuming we're probably at 50 milliliters of acid in there as well. Now the equivalence point, the other word we need to identify, is called the end point of the titration. The equivalence point and the end point don't always line up, but the end point is when we have the color change. So the change in color is called the end point of the titration. The equivalence point is when we have equal amounts of acid and base. Now what we have is another titration curve, and we're going to be looking at quite a few titration curves here. So notice there's some differences here. Notice our initial pH. So one difference is the initial pH. If we're trying to identify these apart. The initial pH is a bit higher. That's because this is a titration of a weak acid. So we have a weak acid that we're titrating with. So we titrate it. Notice the curve starts going up a bit quicker. Notice this was slower to go up. The pH started lower, and we are slower to go up. Here we have a spike right away. We start going up. We'll ignore here the buffer zone for a moment, and we're going up, we're going up. We still have a sharp peak and a plateau here. Notice this finishing pH is still relatively high, so it's a weak acid being titrated with a strong base titration in this one. So a couple points that we find that we can tell this is the initial pH, that immediate jump in pH, and also notice the equivalence point. The pH is 8.73, so at the equivalence point, because we have a strong base and a weak acid, the equivalence point is not at 7. It's not at 7. It is slightly higher because we have that strong base. So we have also a heightened equivalence point where the pH is 8.73. The other value that we want to pick off here is what's called the half equivalence point. The half equivalence point is literally at half the volume of the equivalence point. So normally we'd find that inflection point on the graph, the equivalence point. We draw the line down at half of that volume. So if we're at 25, then we have to go to 12.5 right here. That is going to be the half equivalence point. We can do the derivation, but right now we just want to know that at the half equivalence point, the pH of the solution, which is right here, the pH is going to equal the pKa. So we have to say, well, what is the pKa? Well, the Ka here is the equilibrium constant for the acid. Remember, we had the Kw for water, and that was the hydrogen ion concentration times the hydroxide ion concentration for water. Remember, that was 1 times 10 to the negative 14th. Well, that's the equilibrium constant for water. What we're going to be looking at with these, especially when we have weak bases or weak acids, is we're going to be looking at the equilibrium constant for that acid. So first, we'd have to write a generic equilibrium constant for an acid. So say I had a generic acid here, H, a hydrogen ion bonded to some anion. And this is a weak acid, so it's in equilibrium. We have hydrogen ions, and we have its anion in solution. So if I wrote the equilibrium constant, and don't worry, we have a whole chapter on equilibriums. So again, we're not going to spend a lot of time. I just really want to show you. You're not going to have to write a lot of equilibrium constants at this point, but you do need to be aware of them. So if I wrote the equilibrium expression for just a generic weak acid reaction, what we have is, again, the concentration of the products over the concentration of the reactants. So notice, if this is a stronger acid, it's going to dissociate more. We'll get more of these. These values on top will go up, the one on bottom will go down, and our Ka will be bigger. So the bigger the Ka, the stronger the acid. That's all I want you to know about it right now. So that's how we can tell the strength of the acid, and we can identify the acid is based on the Ka. So that's what makes these type of titrations so important, is because we can look for the half equivalence point when we're working with these weak acids. The pH is going to equal the pKa, and notice for this one is 4.76. So you might wonder, well, what is a pKa? Well, a pKa, similar to a pH, is the negative log of the Ka value. So in this one, it's giving me the pKa, but typically what I'd want is the equilibrium constant itself. So the Ka, just like we rearrange pH, would be 10 to the negative pKa, or in this one, 10 to the negative, what is that value? 4.76. And then we could look it up on a chart, and we could identify what the acid is based upon its equilibrium constant. Pretty slick. We'll do a little bit of that. Don't get too terribly worried. It's actually not too terribly strenuous at this point. Okay. So let's look at these graphs together just so we can pick off the differences. Again, this is a strong acid, strong base titration. Notice the equivalence point, and this is the one of this graph. I should draw this one in green. Notice they overlap a bit up here. The equivalence point is at 7. Again, it starts with a really low pH. If we have a weak acid, the pH starts higher. It's a quicker jump in the pH. The equivalence point is at a higher pH, but again, it levels off with that strong base that we're titrating it with. Now, notice something that they have on here is on this chart, they have the regions of color changes for a couple different indicators. So notice this one, phenolphthalein, the one we're so interested in and we use so often, really changes between a pH of 8 and 9. So it doesn't change around a pH of 7. So typically the best use of phenolphthalein is if we have this weak acid, strong base type of titration, because in that one the equivalence point is going to lie right in the range of the indicator, and that's what we want for a titration. We have to, if we know it's a weak acid, or a strong acid, a strong base, weak base, we want to pick an indicator where the equivalence point will lie right in the region of its color change. Now notice for a strong acid, strong base, the equivalence point is closer to 7. And now notice methyl red is down here. This is probably actually not necessarily the best choice for this one, but it's the one they show here. If we were to choose one where that equivalence point was right in the middle again, we'd probably go back and pick that bromothol blue, which has a nice color change right around 7. That would probably be ideal for a strong acid, strong base. So we just want to identify the different titration curves, what they're going to look like. Notice we do have some other curves, so let's go through these. Sorry, they're a little crooked. That's awkward. So notice we have a strong acid, strong base. Notice very steep jump. pH starts really low, finishes really high. That's characteristic of a strong acid, strong base. This is what we're looking at. In the other graph was a weak acid, strong base, and this one's a little bit even kind of overestimated. Look at how high that pH starts at a pH of 5.5. Notice still a jump and a plateau out at a high pH. If we have a strong acid, weak base, notice the pH will start low, and if we're titrating with that weak base, again, I don't really ideally like this. This would go up really slow. It should be a slow curve, goes up, but notice the key factor is it finishes with a pH that's much lower, and actually the equivalence point of this is probably going to be below 7 because it's a strong acid titrated with a weak base. So here the equivalence point is above 7, here it's at 7, here it's below 7, and if we have a weak acid and a weak base, we're just going to have a general curve, and it's going to be, ideally the pH, the equivalence point is going to be around 7, but it's going to be hard to pick that equivalence point because we don't have that steep jump in pH. Okay, some questions finally. Name an appropriate indicator. Well, we can look at our chart. I'm going to skip through that one and do just the calculations because we do have to also do some solution calculations to figure out what the concentrations of our acids are as well. So we still need to do solution chemistry and stoichiometry. Solution stoichiometry, I guess, is the best word. It says we have HCl. It's required to neutralize 30 milliliters of an aqueous solution of NaOH. What is the molarity of the NaOH? So we first have to write an equation, HCl and NaOH, react, strong acids, strong bases, acid-base reactions are going to give us water, and they'll give us whatever the salt is. This is a classic reaction, so hopefully we know what's going on here. So we have a certain amount of HCl. I'm going to start with that, and I'm going to put it into liters just to start. 0.02 liters of HCl. And now I want to change it to moles, so I'll use the molarity. 0.01 moles per liter. So 0.01 moles. No, that's not right. I don't want moles on the bottom. That wouldn't make any sense. I wouldn't cancel out my liters. So 0.01 moles of HCl. Thank you for catching that for me. Over 1 liter. That's its concentration that I'm punching in. Now where do we go at this point? We look to the equation. Notice this one's 1-to-1. Sorry about that. This one's 1-to-1. So 1 mole of HCl is 1 mole of NaOH in, again, this balanced reaction. That's why we need a balanced reaction. Might be different if we have a polyprotic acid or something to that effect. So right now, let's take a little break. We have liters of HCl canceled. We have moles of HCl canceled. We have moles of NaOH. And what do we want? Molarity. Again, what molarity is moles per liter. We already have moles of NaOH. We want moles per liter of NaOH. So I'm going to put the volume of NaOH we used on the bottom because we want moles over liters. So I'm going to put it on the bottom, 0.03 liters of NaOH because that's the sample we took. Notice I have nothing on top, and that's okay. I'm just dividing by this value so I can get moles per liter. As long, again, as we know the units we're trying to finish in, we can do the calculation. So what I get is an answer of 0.0067 molar NaOH. One thing I might want to look at is, does that make sense? Well, we had 20 milliliters of 0.01 HCl, and it took 20 milliliters to titrate 30 milliliters of that NaOH, so that NaOH molarity, it should be a weaker, lower concentration than our HCl, which it is, again, slightly. Okay, one more. It says, suppose we have 20 milliliters of calcium hydroxide, and it's required to neutralize 12 milliliters of aqueous HCl. What's the molarity of the HCl solution? Again, we always start with our balanced equation. And you can tell, hopefully right off the bat, how this one's going to be different. Is we have calcium hydroxide, which has 2 hydroxide ions. So now we're going to have a ratio that's not 1-to-1. When we write it out, we will have a 2-to-1 ratio. So you need to put a 2 in front of the water as well. So there's a 2 here, there's a 2 here. So we have a different balanced equation, but we'll solve it the same. We'll start with what we have. We have 0.02 liters of our calcium hydroxide is what we used. The concentration of that calcium hydroxide, again, I'm going to put the moles on top. I won't be tricked this time. 0.1 moles of our calcium compound. I'm just going to write calcium in 1 liter of the calcium solution. Now at this point, again, the ratio is 1-to-2. 1 mole of our calcium hydroxide solution, I have room so I'll write it out, is going to react with 2 moles of our HCl solution. Now notice I have moles of HCl, liters of calcium hydroxide, moles of calcium hydroxide finish. I have moles of hydrochloric acid, but I don't want moles of hydrochloric acid. I want the molarity of it, so I need the moles per liter. So I have to divide that number by the amount that of my sample, which was 0.012 liters when I change that in. So that gives me a 0.33 molar solution of hydrochloric acid. And that's it. So very similar to our solution stoichiometry. The only difference is we're working with acids and bases, but we do it the exact same way.